What's up, Chem Peeps? Who is ready for a thermo free response? A student was assigned the task of determining the enthalpy change for the reaction between solid magnesium oxide and aqueous hydrochloric acid, represented by the net ionic equation above. The student uses a polystyrene cup calorimeter, fancy, and performs 4 trials. Data for each trial are shown in the table below. Boom! Part A. Which is the limiting reactant in all 4 trials? Hydrochloric acid or magnesium oxide? Justify your answer. Alright, as I examine my 4 trials, I noticed that I used the same volume of 1 molar hydrochloric acid in each trial. I also noticed that the largest amount of magnesium oxide that is used is 0.50 grams. So, if I'm trying to determine the limiting reactant, there are actually a couple different ways that you can do this. I'm going to show you one way, but as long as you justify your answer, you're good to go. First, let's start with the hydrochloric acid. We have the same amount in each of the trials, so it doesn't really matter here. I'm going to use my molarity equation to convert to moles of HCl. Easy enough. Don't even need a calculator here. We're using 0.10 moles HCl. Next, I've got 2 different amounts of magnesium oxide that I'm given within the 4 trials. I'm going to use the 0.50 grams because that's the one that could potentially make the most product. I'm going to convert to moles and jump to my calculator. 0.50 times 1 is divided by 3.30. We get 0.012 moles magnesium oxide. Again, anytime I'm doing a limiting reactant type problem, I always like to figure out how much product could potentially be made from each reactant. But I know some of you are probably like, Boylan, I know how to do this. Why are you doing so much work? Totally cool. Just make sure that you justify your answer. Alright, so if 0.1 mole of HCl completely reacted, I'm going to determine how many moles of water could potentially form. My ratio is 1 to 1. So I could make, if I used all of that HCl up and it was the limiting reactant, 0.10 moles of H2O. Let's do the magnesium oxide. Remember, if you do it this way, you always want to compare the amounts of the same product. Here my ratio is 2 to 1. Boom. Wait a minute, I thought we were talking about HCl, not H+. What are you doing, Boylan? Where's the HCl? Remember that hydrochloric acid is a strong acid. It's going to completely ionize in solution. It's not located here because this is a net ionic equation. Chloride ion must be a spectator. Watching it happen. Quick jump to the calculator. I get 0.0062 moles H2O. So be sure to answer the question. MgO is limiting. MgO produces the least amount of product. Boom, 1 point. Part B. The data in one of the trials is inconsistent with the data in the other 3 trials. Identify the trial with inconsistent data and draw a line through the data from that trial in the table above. Explain how you identify the inconsistent data. Alright, as I examine my data table here, again recognize that our volume of HCl is the same in each trial and it's going to be in excess in each case. So let's focus in here on the masses of the magnesium oxide. In the first trial, in which we use 0.25 grams, we see a temperature increase of 1 degree Celsius. Trial 2, we have doubled the amount of magnesium oxide, and we see approximately a 4 degree Celsius increase. Trial 3, back to 0.25 grams, and we see a 2 degree Celsius increase. Interesting? I'm using the same mass as trial 1, but my increase has gone up 2 degrees instead of 1. And then finally, trial 4, we're back to 0.5 grams. My temperature increase is again about 4 degrees Celsius. So, as I look to identify the trial with inconsistent data, I'm going to draw a line through trial 1. Let's answer this. Trial 1 is inconsistent. Explanation. The temperature change should be directly proportional to the amount of limiting reactant present. In trial 1, the temperature change is 1/2 the expected value compared to trials 2, 3, and 4. So again, as you look at the data here, let's examine trials 2 and 4, where we add 0.5 grams of magnesium oxide. Notice that we get a temperature change of 4 degrees Celsius in each example, approximately. If I'm going to add half the amount of magnesium oxide, our limiting reactant, we would expect half of the temperature change, which we get in trial 3, an increase of only 2 degrees Celsius. But in trial 1, instead of increasing 2 degrees Celsius, we only see that increase of 1 degree Celsius. For parts C and D, use the data from one of the other 3 trials, i.e., not from the trial you identified in Part B above. Assume the calorimeter has a negligible heat capacity and that the specific heat of the contents of the calorimeter is 4.18 joules per gram degree Celsius. Assume that the density of the hydrochloric acid solution is 1.0 grams per milliliter. Part C. Calculate the magnitude of Q, the thermal energy change, when the magnesium oxide was added to the 1 molar HCl. Include units with your answer. Alright, I'm going to go back up to my data table here. I'm going to grab some data from trial 2 and plug it into my Q equals MCAT equation. For the mass of trial 2, be cautious. Recall that we're using 100 milliliters of HCl, and we're told to assume that its density is 1 gram per milliliter. So if I have 100 mils of HCl, I have 100 grams of HCl, and I have 0.5 grams of magnesium oxide. So I want to make sure that I'm including the total mass of the solution, or the HCl and magnesium oxide combined. So my mass is 100.50 grams. HCl plus MgO. Even though this is not pure water, it's an aqueous solution that is mostly water. And we're told to assume that the specific heat of the contents of the calorimeter is 4.18 joules per gram degree Celsius. Boom! And then finally, our temperature change for trial 2, final minus initial, temperature change 4.1 degrees Celsius. Boom! Calculator! 100.50 times 4.18 is times 4.1 is to 2 sig figs here. Q equals 1,700, watch your units here, joules as my thermal energy change. If you want to represent that in kilojoules, it would be 1.7 kilojoules. Alright, now we were only asked to use one of the trials. In this video, I'm going to include an example from a second trial just to drive home the concept that we were asked to think about in Part B. So I'm going to do the same calculation. This time though, I'm going to use trial 3, where we only used 0.25 grams of magnesium oxide. Again, MCAT. Boom! Be cautious here. Your mass value is going to be 100.25 grams. Specific heat is still going to be the same. My temperature change though, notice, 28.1 minus 26, only 2.1 degrees Celsius. Calculator. 100.25 times 4.18 is times 2.1 is Q equals 880 joules, or 0.88 kilojoules. Now again, you only have to do this one time, but I did it twice here so that you can recognize that the thermal energy change is roughly going to double when we double the mass of our limiting reactant. Notice that our temperature change doubles as well. Part D. Determine the student's experimental value of delta H for the reaction between magnesium oxide and HCl in units of kilojoules per mole of reaction. Again, you only have to do this calculation once, but I'm going to do it twice to drive home a really important point. First, I'm going to bust out my amazing art skills. Boom, here's my coffee cup calorimeter. Excuse me, polystyrene. Fancy. In it, I have my solution and my temperature probe. When we determine the thermal energy change in Part C, we got a positive value for Q. And as you think about why, I like to think of it as the heat was being absorbed by the temperature probe. So it makes sense that our Q values are positive. However, in Part D, as we're asked to determine the experimental value of delta H for the reaction is actually giving that heat off or losing heat. So because the reaction itself is actually giving heat off, we need to keep in mind that delta H of the reaction is equal to the negative of Q over the number of moles of our limiting reactant. Now, if you're like, what? Hang tight, let me work through this problem, and I think it'll make a little more sense. So for that second trial, if I'm going to calculate the enthalpy change for the reaction, it's going to be equal to negative 1.7 kilojoules over, recall that for trial 2, we're working with 0.50 grams of MgO. So it's going to be 0.50 grams divided by the molar mass of MgO, which is 40 0.30 grams. So I'm sort of converting to moles here within this calculation. So negative 1.7 divided by 0.5 over 40.30, close parentheses, inch. To 2 sig figs, I get 140 kilojoules per mole of reaction. Now that might not quite do it, so I'm gonna do it again here. But this time, I'm going to use the information from trial 3. And remember that in trial 3, we're only using 0.25 grams of MgO. So delta H of the reaction is equal to negative 0.88 kilojoules over 0.25 grams divided by my molar mass of 40.30 grams. Let's jump to the calculator here. Negative 0.88 divided by 0.25 divided by 40.30, close parentheses, inch. Notice that, whoops, I forgot my negative. Notice that to 2 sig figs, the enthalpy change for this reaction is negative 140 kilojoules per mole. All right, let's step back and just recap. In part C, you're asked to calculate the magnitude of Q, or thermal energy change. We ended up with a positive value. And again, think of it as our thermometer absorbing heat. So we would expect a positive Q value here. The enthalpy change for the reaction is going to have the same magnitude, but the opposite sign. Again, think of it, thermometer absorbing heat, which is why we got that positive value. The reaction itself is releasing heat. So we would expect a negative value for the enthalpy change of reaction. Notice that we do not get the same value because we're starting with a different amount of the limiting reactant. The more limiting reactant we have, the larger the temperature change and therefore the greater amount of heat. But in part D, we're asked to determine the enthalpy change in terms of kilojoules per mole of reaction. And so what we do is we take those heat values that we determined in part C and we divide it by the number of moles of our limiting reactant. And so even though we had a greater amount of heat released in trial 2, we were using a larger number of moles of our limiting reactant. So this value, our enthalpy change for the reaction then, is often what you see written in next to your equation, delta H reaction equals, for example, negative 140 kilojoules per mole. It's like for 1 mole of magnesium oxide, I would get 140 kilojoules of energy released. But I wasn't using 1 mole, I was only using 0.5 grams and 0.25 grams. So I got a lot less than 140 kilojoules of heat. Woo! Tricky stuff. All right, moving along, part E. Enthalpies of formation for substances involved in the reaction are shown in the table below. Using the information in the table, determine the accepted value of delta H for the reaction between MgO and HCl. Easy enough, we have a formula for this. We're given heats of formation. To determine the enthalpy change of the reaction from heats of formation, simply recognize that's equal to the sum of the heats of formation of the products minus the sum of the heats of formation of reactants. I'm just gonna bring our equation down to make it a little easier to work with. My product, 1 mole magnesium ion, plus my other product, water, also 1 mole. I'm gonna subtract the sum of my reactant heats of formation. Got 1 mole of MgO, add to that, be careful here, 2 moles of hydrogen ion. Now you might be thinking to yourself, well, wait a minute, why do I have to be careful about this? It's just 0. Well, in this case, you were actually awarded a point for the correct setup. So I know you're under pressure, time constraint, but always, always, always write out what you would do to solve the problem. All right, quick jump to the calculator. Negative 467 plus negative 286 is negative 753 kilojoules per mole minus negative 602 kilojoules per mole. Subtracting minus negative 602 is delta H of reaction is equal to negative 151 kilojoules per mole. Boom. Finally, part F. The accepted value and the experimental value do not agree. If the calorimeter leaked heat energy to the environment, would it help account for the discrepancy between the values? Explain. All right, let's answer this first. Yes, here comes my explanation. The experimentally determined value of delta H was less negative than the accepted value. Again, recall that we determined that this student's experimental value of delta H was negative 140 kilojoules per mole. but the accepted value is negative 151. It's less negative than what it should be. In other words, we would have expected a greater amount of heat to be released. If heat had leaked from the calorimeter, then the delta T of the contents would be less than expected, leading to a smaller calculated value for Q and a less negative value for delta H. Error analysis. Always go back and think about the lab. Think about, what was I measuring in the lab? What was I measuring that could potentially cause this error? What would cause me to get a less negative value for delta H? So think about what you measured in the lab, in this case, the initial temperature and the final temperature, and then what you use those measurements for to calculate. In this case, delta T, and walk them through the calculations that you did to get to your value for delta H. Whew, that was a doozy. Have a fantastic day.